linear sign just tells you about direction, whether it's going this way or this way, and Lenz's law will tell you what that is. Okay, that's our current. How do we figure out how to map this thing out as a function of time? Well, first off, we need to think about how the area is changing as a function of time, right? It's starting to ramp up quite quickly until it gets to that point, and then it gets diminishing returns, right? It starts to change less rapidly on the backside. And so it turns out the maximum current is going to be right at the halfway point, right when this square loop gets there. Okay, when it gets to the halfway point, that's when it is a maximum. And so we need to figure out when that happens in time. All right, to do that, let's look at this triangle again. If I think about this triangle now, this side is L. What is this side? Well, this is a 1, 1, root 2 triangle, so this side down here must be L over root 2. So how long does it take for this thing to advance that distance? All right, that's not too bad. It takes a time equal to how far you've gone, L over root 2, divided by how fast you do it, V. This is the time to reach the peak of the current. Okay? And so now you can figure out what the peak current is. I peak is going to be this thing, negative V times 2 times V squared times T peak all over R. And let's not worry about the sign, so we're just going to say the magnitude of I, and then I'm going to take off this negative sign right there. And we'll say the magnitude there, and we'll take off that negative sign right there. Okay? This is how you calculate what the peak current is. And now you can plot this thing out as a function of time. Here's I. Here is T. And what does it look like? Well, it goes up until it hits I peak. And that happens at a time T peak. And then it goes down linearly until it comes back down to 0 in the same amount of time. Okay? And then it's 0 from there on out. So that's what your curve looks like as a function of time. Okay? You know it has to be symmetric about T peak, because if you ran the whole thing in reverse, it should go up and then down, just like this behavior. All right. Hopefully that's clear. You guys can plug in some numbers and try it out and see what you get. Cheers. Hello class, Professor Anderson here. I want to show you something really cool. What we have right here is we have two solenoids. We have 200 wraps of wire on this solenoid, we have 200 wraps of wire on this solenoid. And if you place them close enough together, one of those solenoids can talk to the other solenoid. Let's see how that works. So right here we have a speaker that's wired to one of the solenoids. We have the other solenoid which has a mini output, and I'm going to plug it into my phone here, and we're going to play some music. Okay. And what you're hearing right now is Marvin Gaye coming through the speaker that's coming through this system right here. How do we know for sure that that's really happening? As I pull it further away, it can't get as much signal from the other one, and so it starts to lose the volume. And as I get closer, the volume goes up. In fact, there's more magnetic field flux going through the second coil from the first one when they're right next to each other. But if we know a little bit about magnetic field flux, we know that it depends on the orientation of the coil. So let's see what happens when we rotate the coil. In fact, it goes away. It goes to 0 volume. And if I keep going, it comes back. That's pretty cool. Let's try one more thing. Let's put something in between the two and see if we can block the signal. Okay, so here's a plastic tray. Doesn't seem to change it at all, does it? Yeah, that electromagnetic wave, that beam is going to go right through the plastic. But what if I take a big piece of metal? Definitely affects the signal. Almost sounds like we're underwater now. Alright, so that is what's going on. Cheers. Okay, what is the deal with geometric optics? That pen's out. So the idea with geometric optics is just that. We're going to talk about optical elements, and the important components of the optical elements is the geometry of the setup. Okay? And this entire chapter can broadly be categorized under one following statement. Light is a ray. All right, we learned about light a little bit in the last chapter when we talked about electromagnetic waves. We said that electric fields and magnetic fields can oscillate together and they can propagate along as an electromagnetic wave. Okay? That is what we call light. Specifically, light refers to sort of the visible portion of the spectrum, but a lot of times you hear physicists refer to the entire electromagnetic spectrum as light. Okay, so electromagnetic spectrum is pretty big. You've got X-rays at the very short wavelength scales, you've got radio waves at the long wavelength scales, and somewhere in the middle you have the visible spectrum. You got the Roy G. Biv, right? The red, the yellows, the greens, the blues, the indigos, the violets. So light is a ray. What does that mean? It means it travels in a straight line. Okay, now there's a caveat there, which is the following. In free space. Pretty soon we're going to talk about what happens when it meets up with glass or water, and then you can see that the ray will actually bend. But in free space, light travels in a straight line. It's a ray. So when you think about a star, here's a distant star. Okay, what is that star doing? Well, it's spitting out electromagnetic radiation in all these different directions. And each little bundle acts like a ray. And so if you're sitting down here on Earth, and you're looking up at that star, there is a ray that came directly to you. And it's kind of weird to think about, but that little photon, that bundle of energy that left the star, however many millions of years ago, traveled in a straight line all the way across free space, all the way to your eyeball. You detected it, and it was gone. Okay, so that was the source of the ray. This was the sink of the ray. Started there, ended there, traveled in a straight line. The fact that it travels in a straight line lets you determine exactly where that star is. Now, it gets a little more complicated once we get to general relativity, but for now, just consider those rays moving really in a straight line. If you looked up, came from there, that must be where the star is. All right, what about when light rays bounce off of stuff? So let's say that that light ray comes at us, but it's not going to hit your eye. It's going to bounce off of a mirror. So we have a mirror right here. Here's a mirror. Can you guys see that? Probably if I look just like that, you can maybe see my reflection. Can you see my reflection? It's a really dirty mirror. Okay, that's a mirror. What is a mirror? A mirror is very simple. It is a coating of aluminum or silver on glass. Okay, there's a glass substrate, and on that glass substrate, you provide a little bit of aluminum or silver. If you have a lot of money, you can buy gold mirrors, right? You can put gold foil down onto a glass substrate. And so it looks like this. Here is our glass. And then right on top, there's a very thin coat of metal. Okay, and it doesn't have to be very thick at all. The metal is what does the reflection. So when a light ray comes in, here comes our light ray. It hits the mirror, and it bounces off. Okay. Why does that happen? Why does light bounce off of this mirror? And the combined two things here, the glass and the metal, is what constitutes the mirror. Why does that happen? It happens because we know that light is made up of electric fields and magnetic fields. And when those electromagnetic fields hit the metal, the little charges in the metal start to vibrate. And they vibrate at exactly the same frequency as that light ray that was coming in. And it re-radiates that stuff out into another ray at the same frequency. Okay? This is why you have to have metal there. If you have an insulator, like a piece of wood, it doesn't reflect the light ray. And that's because those little charges in the wood can't move quite as easily as the charges in the metal. So the metal is, in fact, what does the reflection. Metal causes that reflection to happen. What is the purpose of the glass? Let me ask you guys. Chime in on the chat room and tell me what the purpose of the glass substrate is. I answer. The purpose of the glass substrate is purely to keep the metal flat. So if I think about a piece of metal like this, it can be kind of flimsy, right? It's easy to bend. And if I bend this, you can see the reflection change shape, okay? Think about when you open a brand new can of aluminum foil, right? It comes out and it looks like this. And it doesn't make a very good reflector. But if you pull it out very slowly and lay it on the table, then it's flat. And so that's it. The whole purpose of the glass is to keep it flat. There's an additional purpose, which is to keep it from oxidizing. So typically when you look in the bathroom mirror, there is metal coated on glass, but the very front side is glass. Then there's metal behind it, and then there's some other sort of protective backing on it. The glass is really just there to keep it flat and to keep it from oxidizing. The back substrate just keeps it from oxidizing, which is the law of reflection. And we sort of alluded to this in our first picture, which is the following. Let's say we have a mirror, okay? We know that a mirror is made up of shiny metal. And let's say that we have a ray coming in at some particular angle. And when we draw these angles, we always draw it relative to the surface normal. That incident angle, we call it theta I. Now, going out the other side, we of course have a reflection. And if this is a nice flat metal surface, then that reflection is at theta R, and the law of reflection says the following. Theta I is equal to theta R. Incident equals reflected. Remember, they're always relative to that surface normal. Okay, so in the case of the mirror that we just talked about, we said, where is the image? Using this law now, we have to think about how do you form an image in a mirror. So let's draw the following picture. We've got a metal mirror that we're going to make vertical. Let's put in what we call the optic axis, and let's put an object right here. What do the rays from that object do? Well, first of all, how are those rays generated at all? Light illuminates the object, just like light from these lamps is illuminating me. Every single point of me is reflecting rays in all directions. So if this is an object, if this is an arrowhead object, the light that is hitting the tip will go off in all directions. Light that is hitting the base will go off in all directions. Just like when you look at this image of me, light from my cheek is different than light from my nose or my hair, and yet those rays are going off in all directions. You intercept a few of them with your eyeball. So let's think about where the rays will be going from here. Okay? Light comes in, bounces off. We don't have to worry about the light coming in. What we have to worry about is the light bouncing off. So one ray will do this. It will bounce off of the mirror and come back. And if I continue with a dashed line, that is where that ray appears to be coming from. Now, if I think about an observer, here's my observer, then there will be a ray from the tip of this object that comes up and bounces off and goes into the eyeball. And now if I take a dashed line and continue, the point where those two dashed lines intersect each other is where the image is located. So that object has an image that is right here. And so everybody got it right. The image is equidistant from the mirror on the other side. And you know this already, right? When you stand in front of a mirror, you see an image of yourself on the other side of the mirror, the exact same distance away. If you're standing 2 feet away from the mirror, it looks like you have an image that's 2 feet on the other side of the mirror. If you back up further, your image gets further and further away. Okay? As you get closer, it comes closer in. So everybody got that one right. Their intuition was correct that it was indeed answer B on that Coker question. And the way you see that is this idea of the law of reflection. If this ray comes in at this angle, it's going to go off at the exact same angle relative to the normal. And now you just have to follow those lines back. It's kind of weird, but when you see something, you see what you think is where those rays are coming from, right? If the mirror wasn't there, you wouldn't see an image over there. Okay? Putting the mirror there means that it looks like those rays are coming from there. Let's say we're standing in front of the wall mirror, and the wall mirror is not half your height. It is maybe 1/4 of your height. Okay, so here's the wall mirror, and here you are. Okay, and let's move this mirror up just a little bit so it's even with the head of the person. Okay, and the question is the following. If you are height h, and this thing is h/4, how far back do you have to stand to see your shoes? Okay, namely, you're standing next to this mirror, and you can't quite see your shoes. Okay, how far back do you have to go in order to see your shoes? And this thing is wall-mounted. Okay, it's flat. This is our wall. It's a flat mirror. It's perfectly vertical, and you're just going to walk back on a level ground. How far back do you have to go to see your shoes? Questions out there. A lot of people said, oh, it's got to be 2h. Some people said, well, it's 1/4 the size of the mirror, so it's got to be 4h. Let's see if we can think about how this is going to work. What we said was that rays that bounce off a mirror bounce off the exact same angle they came in at. So if we think about the bottom of this mirror and a ray going from the bottom of the mirror to the person's eye, where did it come from? It had to come from about there. Okay. Incoming angle has to equal reflected angle. All right, so at this distance right now, you can see maybe your midsection, right, your belly button. But now let's take this person and let's move them far away and see what they can see. Okay, we'll extend our floor a little bit. And now that person is right here. The light ray that came to their eye had to come at an exact same angle. Okay. Can they see their shoes? No. They see their belly button again. As the person steps back, those rays start to narrow down. So even though you've increased the distance that the ray is traveling, the angle has also decreased. And so when can you see your shoes? Never. You can never see your shoes. If everything is flat and vertical and horizontal floor, you can never see your shoes, which is kind of weird to think about, right? If I'm standing looking in the mirror, sure, I must be able to back up enough to see my shoes. That's not the case. Okay, you'll always see the exact same point on your body no matter how far back you go. So what is the difference between specular reflection and diffuse reflection? Well, it's pretty much this. If I look in this mirror, can you guys see me in that mirror? There's my eyeball. Okay, you can see my eyeball right there. All right, that is what's called a specular reflection. You can make out my face in that image from the mirror. Diffuse reflection is if I do this. Okay, I fogged up the mirror, and now, while it's foggy, you can't make out my face anymore. So specular is just that. It is a smooth surface. Diffuse is a bumpy surface. Okay, so if I think about a specular reflection, the mirror is nice and flat and smooth. All the rays that come in bounce off at a nice angle governed by the law of reflection. There are, of course, many rays that come in, and they all bounce off, obeying the law of reflection. But a bumpy surface has all these indentations or water droplets on it, like in the case of this mirror. And so when a ray comes in, it hits there, it's going to suffer the law of reflection at that point. The next ray that comes in will suffer the law of reflection at some other angle. And so all these incoming rays get scrambled into all these other directions, and that's why you can't make out an image in a diffuse reflecting mirror. Now, you're all familiar with this, right? You're all familiar with that problem. When you go to take a shower in the morning, and you get out and go to your bathroom mirror, and you need to shave or put on your makeup, right? You look in the bathroom mirror, and you can't see yourself very well, because it's all foggy, like that. Okay? How do you clean it off? You go like this, right? You grab a washcloth, you take away all those water droplets, and now you make a nice, smooth surface again. So, here's a little beauty tip for you. That works fine, except it only lasts for about 30 seconds, right? If you take a washcloth and wipe off the mirror, 30 seconds later, it's full of moisture again, and there's all these water droplets all over it. You can't see yourself again. That's because you just took a hot shower, there was lots of water molecules floating around in the bathroom, and they're looking for a place to land. They're going to land everywhere, on the walls and on, other things in there. They're also going to land on the mirror, okay? But they don't like to land on things that are hot. That hot surface will bounce those water molecules back off of it. So if you wipe your bathroom mirror and it gets foggy again, the way to prevent that is to take your hairdryer and just heat it up for about 30 seconds. Wipe it, heat it up with the hairdryer for 30 seconds, and now it'll stay clear for the next few minutes. So you can finish applying your mascara. Sean, what kind of mascara do you use? Okay, this business of mirrors is kind of cool because, as you know, when you look in a mirror, your image is reversed. In fact, you're looking at me right now, and my image is reversed because in front of the camera, we have a mirror. Okay? Right now, I'm holding up my right hand, but of course to you, this looks like my left hand. Now I'm holding up my left hand, as you can see, that's my watch on my left hand and my ring, but of course to you, it looks like my right hand. That's because mirrors flip left and right. Okay? There's a great YouTube video about the flipping of mirrors, and it's by somebody called Physics Girl. She has a whole bunch of really great videos, physics videos, and she points out that it's not so much flipping left to right, it's flipping plus Z to minus Z. So take a look at that video, it's really good. When you think about light bouncing off of mirrors, it of course bounces at the angle that it came in at. Law of reflection says incident angle equals reflected angle. But what if we have two mirrors at right angles? Okay, so let's take a mirror, and let's take a second mirror and put it right next to the first, and we'll put them at right angles to each other. Okay, so we've made this nice sort of assortment of mirrors here. What happens when a ray comes in? A ray comes in and it bounces off the first surface. Okay, and we know that it bounces at the same as its incident angle, and so it's going to look something like that. When it bounces off the second mirror, it's going to bounce at an angle like so. And to make this really convenient, let's do the following. Let's say that this angle is 45 degrees. And if that angle is 45 degrees, then this angle is 45 degrees. Okay? And if those two angles are 45 degrees, then those two angles are also 45 degrees. Okay? Everything adds up. The outgoing ray is, in fact, parallel to the incoming ray. You might have seen these before, okay? They have these in dressing rooms, and the reason that they put these in dressing rooms sometimes is so that you can see your reflection the way other people see it. The bounce off the first mirror flips you from left to right. The bounce off the second mirror flips you back right to left. So if you stand in front of one of these mirrors and you raise your right hand, your image raises its right hand, okay? It's a very nice way to see what you look like, but there's a much more important feature here, which is the following. Let's say we didn't just do this in 2 dimensions. Let's say we did it in 3 dimensions. If you do it in 3 dimensions, it's called a corner cube, and let's see if we can draw it out. Okay, these are the mirror surfaces. And now, any incoming ray will bounce 3 times and come out parallel. And this thing is called a corner cube. This last ray took a little funny jog there. Straighten that out a bit. Okay, it's called a corner cube. And it's used in physics quite a lot, but you are in fact familiar with this device, okay? I can guarantee you that at some point today, you have come across a corner cube in your regular daily life. Where have you